Welcome to lecture 26 of electromagnetic field and waves. Let's start with a brief review of where we left off last time, and then we'll take it from there. So last time we looked at the characteristic impedance of lossy transmission line. And we basically found that for a lossy transmission line which has a non-zero series resistance R and a non-zero shunt transconductance G, you find a characteristic impedance Z0, which is equal to the square root of R plus iota omega L over G plus iota omega C. And after we derived this, what we further looked at was so we looked at a terminated transmission line. The idea basically being that you have a transmission line, which is of course two conductors, and they're actually terminated with some load impedance ZL at the end. And in the first two lectures on transmission lines, we basically saw how to just analyze the transmission line itself. And what we did last time was that we added a further load at the end, and then we saw what the effect of the load is. And basically what the effect of the load was that we said that you will have some forward propagating V plus of Z and some backwards propagating V minus of Z, right? So we basically discussed that because of the load at the end, because of the termination at the end, we have right and left moving waves, and the left moving waves were reflections of the right moving wave. So we said that V plus of Z is coming from the source. It's being reflected by whatever impedance you have at the end, and then something reflects back, and that's V minus of Z. And basically what we did was we found the reflection coefficient, and we'll get to that in just a second. So the voltage at any given spatial location V of Z, so we saw that V of Z was equal to V plus of Z plus V minus of Z. And the way that V plus and V minus were related, the way the amplitudes were related, was that this becomes equal to A plus, which is the just the amplitude of V plus, e to the minus gamma prime Z, e to the minus gamma double prime Z, plus the reflection coefficient gamma L times the amplitude of the right moving wave A plus, e to the power positive gamma prime Z, e to the power positive gamma double prime Z, right? So this is the right moving, moving in positive Z, and this is the left moving, moving in negative Z. And gamma L was, so this factor gamma L was the reflection coefficient at Z is equal to 0, where Z is equal to 0 is the location of the load impedance. And we derived that this is I said that this is a very, very important derivation. The derivation wasn't important. The final result is important, which is that we saw that gamma L becomes equal to ZL minus Z naught over ZL plus Z naught. So this, of course, is the characteristic impedance of the transmission line, and this factor of ZL is the impedance of your load. And so what we saw was that what we saw is that if ZL is equal to Z naught, then this factor gamma L is equal to 0, and so you get no reflections, right? And this is known as impedance matching. Yeah, a matched impedance, right? And I said that you can actually draw parallels between impedance matching and this reflection coefficient here. So you can actually draw very strong parallels between the reflection coefficient here and the reflection coefficients for electric and magnetic fields, which we derived when we did the Fresnel equations. So when we looked at the reflections at a dielectric, we saw that the difference in refractive indices back then determined how much of the incoming light reflects, and over here the difference in the impedance dictates how much of the light reflects. It's actually it's a very strong parallel, and transmission line theory is actually it draws very strong parallels to Maxwell equations, right? It's an abstraction on top of those. Now this factor of gamma prime, this is 0 for a lossless waveguide, transmission line, and the transmission line is just a special type of waveguide. Right. So I hope that all of this is clear, because what I now want to do is that I now want to look at the power transmitted and reflected. Now let's find the ratio of power reflected to the incident power. So the reflected power is proportional to, it's really understandable, the square of the amplitude of the square value of V minus squared, right? I mean, we can imagine there's some proportionality there. And similarly, the incident power PI can be assumed to have some proportionality with the V plus squared, right? So the ratio of the reflected power to the incident power of the signal, well, you can very well likely believe that it's equal to gamma L times gamma L complex conjugate, which is just equal to mod square of the reflection coefficient. And the reason for this is that most generally gamma L is a complex number, because Z naught or ZL can both or either be complex. So the ratio of the reflected power to the incident power is the mod square, yeah, the complex conjugate times the times the reflection coefficient. So now consider connecting two transmission lines together. So consider this to be our first transmission line, and consider this to be, this is the second conductor of our first transmission line, and this is our second transmission line. Excuse my drawing. Let's say that the first transmission line has a characteristic impedance Z01, and the second transmission line has a characteristic impedance Z02, and we connect both of these transmission lines together, right? So this is transmission line 1 and this is transmission line 2, and if connected both of them together. Now in this case what will happen is that this is the interface between transmission line 1 and transmission line 2, right? And let's say that this is occurring at the location z is equal to 0. So the incoming signal V plus of z will get reflected at this interface, because this is the interface between the two transmission lines, and depending on the impedances of both transmission lines you will get a reflection. And so gamma L becomes equal to Z02 minus Z01 over Z02 plus Z01, right? And so to get maximum transmission between the two transmission lines, Z02 must be matched with Z01, which is why when you're connecting two cables together or two transmission lines together, you want their characteristic impedances to match for there not to be too many reflections. And the same goes for waveguides also, but only if we had enough time in this semester to study waveguides properly. Anyhow, so that's the reflection when you connect two transmission lines together. So the ratio of power transmitted to the power reflected, this ratio, so the ratio of power transmitted over the incident power, or power incident, this ratio becomes 1 minus mod gamma L squared, right? So this is the fraction of power transmitted. So the higher the mismatch between the two impedances, the higher would be the factor of gamma L, and the lower would be the transmission between the two waveguides. Now if that's okay for most of us, then I actually want to start a new topic, and this is a conceptually very revealing topic, and I think a lot of the stuff that we've been talking about should become clear after this. And this is something that's called the voltage standing wave ratio, and we'll be calling this VSWR for short. Now we've seen how the reflections in a terminated transmission line depend strongly on the impedance of the line and the load, right? So we've seen that gamma L is a function of Z0 and ZL. So you can imagine that within a transmission line, within transmission line, you have some forward propagating V plus of Z, and then you equally have a backward propagating V minus of Z, right? And since these two waves can probably have some phase relation between them, what we can imagine is that V plus of Z and V minus of Z will have some degree of interference, right? They'll have some degree of interference amongst one another, and basically what the voltage standing wave ratio, the VSWR technique, does is that it uses this interference to try to find out an unknown impedance. So basically the idea basically is that you have a voltage source over here, this voltage source is connected to a transmission line, right? And this is of course connected to a load ZL. This is an unknown load impedance, and this transmission line, so when you try to find an unknown impedance ZL, one of the ways is using a special type of transmission line which is known as a slotted transmission line. And the idea of a slotted transmission line is that it allows measuring voltage at different points as it has a gap for voltmeter probes, right? So essentially this is the idea. So what happens is that the interference between V plus of Z and V minus of Z, this interference leads to the formation of standing waves. And so you have some standing waves and you have some traveling waves, and the relative amplitude of both can tell you something about the impedance. And this is what we derive properly in the remaining part of the lecture. So here are some example slotted transmission lines, and the idea basically is that you can run a probe along the length of your slotted transmission line, such as this or this, and this basically allows you to measure the voltage at different points. And so what you can do is that you can map the standing waves that form as a result of the interference of the right and left propagating waves, and then you can measure the relative amplitude of the maximum and minima occurring on the standing waves, and this allows you to determine the unknown impedance, let's say, that is, for example, connected to this port, and the source is connected to this port. Yeah, this port and this port. Okay. So that's what a slotted transmission line looks like. Now, so the voltage standing wave ratio would be the ratio of the maximum voltage to the minimum voltage across the transmission line. Okay. So now let's look at some examples. So let's consider some examples. So the first example that I want to consider, let's call this case 1. The first example that I want to consider is a matched impedance. Meaning that ZL is equal to Z0. So the schematic of this scenario would be that you have Vs, which is your source. This source is connected to your transmission line, which is then connected to your load ZL, right? And in this case, we know that gamma L, which is equal to ZL minus Z naught over ZL plus Z naught, becomes equal to 0. So there are no reflections. Right? And the time average voltage, so time average voltage is same at all points in the transmission line. So meaning that if I connect a voltage source to this end, function generator, and at this end I put an impedance which has the exact same impedance as this transmission line, then I get this scenario here, and that scenario gamma L is equal to 0, and so there are no reflections, there's no interference, and so you don't get any standing wave formation, right? And that's the case of a matched impedance. So that's case 1. Let's look at case 2. Case 2 is fun. Case 2 is it's that ZL is equal to 0, and which means that ZL is a short circuit, right? So you have your voltage source here. Now, since we've spent so much time talking about electric and magnetic fields and electric potentials, and so whenever I talk about a voltage, I want you to at least have some idea and think about what this means in terms of an electric field, right? So then this is a short circuit. Now in this case, so this point of course is Z is equal to 0 always. We've always put the location of our load as Z is equal to 0. So gamma L becomes equal to 0 minus Z naught over 0 plus Z naught becomes equal to minus 1, right? So gamma becomes equal to minus 1, but we know that gamma L is equal to V minus at Z is equal to 0 over V plus at Z is equal to 0. So this becomes equal to minus 1. So that means that V minus at Z is equal to 0 becomes equal to V plus at Z is equal to 0. So at any other point, so at any other point, V of Z, let me just change color here. So V of Z becomes equal to A plus e to the minus gamma Z minus A plus e to the plus gamma Z, because A minus is gamma times A2, gamma is just minus 1, right? But we know that gamma is equal to gamma prime plus iota gamma double prime. So V of Z becomes equal to A plus e to the minus gamma prime Z e to the minus gamma double prime Z minus A plus e to the gamma prime Z e to the gamma double prime Z, of course with an I here. Apologies for missing the I before. And so V of Z becomes equal to so if you take A plus common, and so you're basically adding exponent of minus gamma Z to minus exponent of minus, you're adding exponent of minus gamma Z minus exponent of plus gamma Z. So that's actually that's just it's a recipe for a hyperbolic function, right? So V of Z becomes equal to minus 2A plus sine hyperbolic of gamma x, right? Where gamma is just a propagation constant. So that's the phasor, right? That's the phasor. That's the phasor voltage as a function of z. So if that's the phasor voltage, then the instantaneous complex voltage becomes, so V of Zt becomes equal to minus 2a plus sine hyperbolic of gamma x e to the I omega t, right? That's what the instantaneous voltage becomes. And of course the real, the physical voltage is just the real part of the complex instantaneous voltage. So that becomes so V physical of Zt becomes equal to real part of V of Zt. So this becomes equal to minus 2a plus sine hyperbolic of gamma x cosine of omega t, because the real part of e to the power iota omega t using the Euler's identity is cosine of omega t. Now it's interesting that it's so interesting. I write it in a different color, that this is a standing wave, which is remarkable if you think about it. Because why is it a standing wave and not a traveling wave? Because you see, something like cosine of kx minus omega t is a traveling wave. Because if you sit at any given x and you let time pass, you see the wave pass behind you because the phase will change. But you see, this is a standing wave, because if you apologies actually, because I've written x here, I should write one second, I should write z here. Yeah, so if you sit at any given z, time will pass and the wave will move up and down, but there's no like movement of the wave in z per se, right? So this is a standing wave, and when you have a short circuit, what you get is a standing wave. So we've looked at a standing wave in a short circuit condition. Let's now go to the next case, which is the case of an open circuit, and see what happens, right? So we will now do case 3, and I'm doing these cases to just give you an idea of these reflections. And case 3 is that the load is ZL is infinity, and so we basically have an open circuit. Now schematic of the scenario looks something like this. This is your source V here, Vs, sorry. It's connected to a transmission line, and the transmission line just terminates, right? So then gamma L becomes equal to, so it's infinity or infinity essentially, that's 1, right? So if gamma L is equal to 1, so this implies that V minus at z is equal to 0 is equal to V plus at z is equal to 0, right? So V of z becomes equal to a plus e to the minus gamma z plus a plus e to the gamma z, right? So this becomes equal to 2a plus cosine hyperbolic of gamma z. So the physical instantaneous voltage V of zt becomes So Vp of Ct becomes equal to 2a plus cosine hyperbolic of gamma z cosine of omega t, right? So for both open and short circuit conditions, we get standing waves in our transmission line. So we've done these three special cases. Now we're in a position to look at a more, which is let me just call this case 4, and this is a general complex load ZL. So it's neither purely imaginary, nor a pure short circuit, nor matched, nor open, just a general load, right? So just this scenario, this is your voltage source, this is your transmission line, this is ZL, right? Our general load. So at any given point along the line, we know that V of z becomes equal to V plus e to the minus gamma z plus V minus e to the plus gamma z, right? And what we'll do is that, so that much we know, right? What we'll do is that we will consider a lossless transmission line such that, so when you consider a lossless transmission line, if you remember last time, what we get is that gamma becomes equal to 0 plus iota gamma double prime, which becomes equal to iota omega square root of LC, right? We derived this in detail last time. So we can actually write this to be equal to iota times some factor beta, where this factor beta is omega square root of LC. So if I write it like that, then I can write my expression for V of z as V of z becomes equal to V plus e to the minus iota beta z plus V minus e to the plus iota beta z. Honestly, the reason for now talking in terms of this real number beta and having an iota there explicitly rather than implicitly is because you see, hyperbolics are best avoided whenever I want you to understand something. So so I think let's just work with normal trigonometric sines and cosines. Otherwise we'll get hyperbolic functions when we add them. So so that's V of z, and this becomes equal to V plus e to the minus iota beta z plus, now V minus, of course the amplitude is just gamma L V plus e to the iota beta, right? And remember that gamma is a complex number in general. So then by definition, gamma L is ZL minus Z naught over ZL plus Z naught. So and we know that ZL in general is an imaginary, it's a complex number. So this is equal to the magnitude of gamma L times e to the power I5, right? Whatever phase factor this complex number has, if it has any, but in general it can have some. So V of z becomes equal to V plus e to the minus I beta z, right, plus the magnitude of gamma L times e to the I beta z plus iota times phi, right? And we can then further simplify this. But actually, before I do that, let me just call this something. Let me call this equation A, because we need to come back to it afterwards. Anyhow, so simplifying this a bit more, this becomes equal to V plus into e to the power minus iota beta z plus the magnitude of gamma L times e to the I times beta z plus phi, right? Nothing new there. What we can do is that we can divide by a factor of e to the I phi by 2, and if I do that, then what happens is that, so this becomes equal to v of z. I'm just writing v of z. So v of z becomes equal to v plus e to the I phi by 2, a factor which we've taken common because things will become simpler if and when we do this, times e to the minus iota beta z e to the minus iota phi by 2 plus our reflection coefficient gamma L times e to the iota beta z times e to the iota phi by 2. Okay. So this is pretty much just following from equation A there. And now what we'll do is that we will apply an algebraic trick. So we will perform an algebraic trick, and I want you to follow what happens here. It's not a very exciting trick, but it's a convenient trick. What we'll do is that we will add and subtract a factor of v plus into 1 minus magnitude of gamma L e to the minus iota beta z. So we will add and subtract this factor. If you do that, what you get is that v of z becomes equal to v plus times 1 minus mod gamma L e to the minus iota beta z plus v plus mod of gamma L, okay, e to the iota phi by 2. But inside, what we can now write is that we can actually write into e to the minus I beta z e to the minus I phi by 2 plus e to the I beta z times e to the I phi by 2. Okay. So what this algebraic term has allowed to do is that it's basically, so it brought 4 terms essentially into the mix, and it allowed me to separate out these terms here and construct another term over here, right? And what this allows us to do is that we can identify that this is exponent of minus iota beta z minus phi by 2 plus exponent of iota bz plus phi by 2. So you can actually rewrite v of z as, so v of z becomes equal to v plus times 1 minus gamma L e to the minus iota beta z, okay, plus 2v plus mod gamma L e to the I phi by 2 cosine of beta z plus phi by 2. right? So everything then comes into this cosine dependence. And just so that we're on the same page, I just want to reiterate that V plus here is the source voltage amplitude, right? Whatever source that we've connected on the left hand side is the source for V plus e to the I minus e to the minus gamma z, right? Which is why then you have these reflections, and what we're just computing is the net resultant after these reflections. So if you're convinced with this, then the complex instantaneous voltage V of zt, this basically becomes so V of zt becomes V plus into 1 minus mod gamma L e to the minus iota bz e to the iota omega t, right, plus 2V plus mod of gamma L e to the iota phi by 2 cosine of beta z plus phi by 2 e to the iota omega t, right? And with this, if we then take the real part, so if we then find the so if you find the physical, meaning the real instantaneous voltage at any point in the transmission line, so this becomes so V physical as a function of zt becomes equal to the real part of V complex zt, right? So this becomes equal to V plus into 1 minus mod omega L, which is the reflection coefficient, into cosine of omega t minus beta z, that's a traveling wave, plus 2V plus into mod omega L cosine of beta z plus phi by 2. Remember, phi is the phase of the reflection coefficient because the reflection coefficient was a complex number, times cosine, times cosine of omega t plus phi by 2. Apologies for the rather longish expression, but we have two terms here. So we have this term, and we have, let me use a different color for this. So we have this term, we have this term, okay, and this term is a traveling wave, and this term is a standing wave. Now, if you remember that we just looked at a short circuit before, so imagine that the magnitude of gamma L is 1, as we had for an open circuit voltage, for an open circuit load. Then 1 minus 1 becomes 0, the traveling wave becomes 0, and you only have a standing wave. Similarly, if you have a short circuit, the magnitude of when you had a short circuit, the gamma L was minus 1. So the magnitude of gamma L is 1. So 1 minus 1 once again gives you a 0 for the traveling wave. So for a short circuit and for an open circuit, you can see from here that you only get a standing wave. And for a general load, you have a traveling wave plus a standing wave, as we have here. So if I were to just draw this pictorially for you, what's happening here is that you have your transmission line, right? And this transmission line has some load ZL connected at the end, and as a result, what you have is so you have a forward propagating. Actually, let me just use a different color for this. So you have a forward propagating traveling wave. So this is traveling wave, and this is moving in this direction. And on top of the traveling wave, what you have is some standing wave, so you have a standing wave, and this is a standing wave, and the standing wave is not traveling, and the standing wave is the result of the superposition of V plus and V minus, right? And so in some cases you only have a standing wave, in some cases you only have a traveling wave. For example, if you have a matched impedance, then you have only a traveling wave. If you have a short circuit and open circuit, you have a pure standing wave, and usually you have a superposition of both in any waveguide. It's pretty cool if you think about it, that in any coaxial cable you connect, and if it's not connected perfectly, then there's like interference, taking place within that line. It's pretty cool if you think about it. Plus, if you think about connected to things such as the skin depth and such, which we've discussed before, so I think whole doors open up in our minds, right? Anyways, so we've placed this at z is equal to 0, and let's try to find out where the so let's try to find out where, at what locations do the maxima and minima occur, right? Let's try to figure this out. So let's go back to equation A. Now equation A basically stated that V of Z becomes equal to V plus times e to the power minus I beta Z plus the magnitude of gamma L times e to the I of beta Z plus phi, right? That's what the question was telling us. Now, the minimum amplitude occurs when the phase difference between this term and this term is equal to pi, right? So the minimum amplitude occurs when phase difference so let's do the minimas first. So minima occur when both exponentials have a pi phase difference between them, or an odd multiple of pi, right? So what that means is that the phase difference, right? So the phase difference would be so minus beta Z, which is the phase of this guy, minus, because the difference, minus beta Z minus phi. Beta Z minus phi is the phase of this. Beta Z plus phi, but we are subtracting it, so it's phase 1 minus phase 2. This becomes equal to an odd integer multiple of pi, right? So times 2m plus 1 into pi, where m is some integer 0, 1, 2, 3, so on and so forth, right? So what this gives us is that minus 2 beta Z becomes equal to 2m plus 1 times pi plus phi. So Z becomes equal to minus 1 over 2 beta whole into 2m plus 1 pi plus phi, right? And this is z minimum, and these are the values of z for which minima occur. So for any value of z which satisfies this for any given m, you will have your minimas. Okay. For minimum amplitude, the minimum amplitude might not be 0, right? But it will be whatever the minima is, because the difference between these two terms will be the highest. Now, similarly, moving on, just one thing, that when the difference between the two terms is pi, then you have a minus sign here, right? And so it's v plus minus gamma times v plus. Anyway, we'll come back to this. Okay, so we know where the minima occurs. Let's look at where the maximas occur. So the maximas occur when the phase difference becomes a multiple of 2 pi, right? When they're in phase. When the left and right traveling waves are in phase, obviously. So then minus beta z minus phi becomes equal to 2m pi, right? Or so z becomes equal to 2m pi plus phi times minus 1 over 2 beta, and this is the location of z maxima, and of course m is an integer, so on and so forth, right? So when z equals minus 1 over 2 beta into 2m pi plus phi, that's when you have your maximas, right? And in the other location you have your minimas. Now we know where the maximas and the minima occur. So now what is the voltage at the maxima and the minima? So the voltage at z minimum that voltage, if you have a look, so we'll call it V minimum, which occurs at Z minimum, is if you substitute this Z back into the equation, you'll find that V minimum becomes equal to V plus times 1 minus the magnitude of gamma L, and the voltage at Z maxima, which we'll call V max at Z max, becomes equal to V plus 1 plus mod gamma L, right? So that's the so you plug Z back into the equation and you can find the time dependent voltages. Now coming back to where we started off, which was the voltage standing ratio standing wave ratio, which we call VSWR. So VSWR, then it's typically in a lot of textbooks it's given the symbol S. So S becomes equal to the voltage at a Z max, the maximum voltage, over the voltage at Z minimum, the minimum voltage. And so if this is the maximum voltage and this is the minimum, sorry, this is the maximum voltage, this is the minimum voltage inside your waveguide, so, or your transmission line. So this ratio becomes equal to 1 plus mod gamma L over 1 minus mod of gamma L. So, and the last thing that I want to do is general case S becomes equal to, I'll just write it down again for you, 1 plus mod gamma L 1 minus mod gamma L, right? And so what you do is that, so you measure voltage across your slotted transmission line, and you find Vmax and Vmin. Once you find Vmax and Vmin, you can find the amplitude of gamma L. So this allows you to find mod gamma L. So once you have the mod gamma, then so all you need then is phi. So you can find the phase using the location of Zmin and Zmax. So using the location, so you can find phi. So then you will have gamma L, which is equal to mod gamma L e to the I phi. So S allows you to find this, and using the location of Zmin and Zmax, you can find e to the I phi. And once you have this, then you can find ZL using the relation that gamma L is equal to ZL minus Z naught over ZL plus Z naught. So the reason that I chose this particular application of slotted lines and the voltage standing wave ratio in this short amount of time that we had to study transmission lines is because the physics of standing wave formation and the idea that in most general transmission lines you have back reflections at the termination point, and those back reflections propagate back and they create some level of standing waves within your transmission lines. And so you really have to think about how much power is being transmitted and how much power is being is forming these standing waves and going back towards the source. And also it's an interesting application because it allows you to find the complex impedance, any unknown complex impedance. So it's one very useful method in both microelectronics and basically radio frequency RF analysis. So this pretty much covers everything that I wanted to cover for transmission lines. I wish we had more time. Then we would have basically done certain a lot more specifically with perhaps with regards to Smith charts, with regards to some special cases of transmission lines, half wave lines, quarter wave lines, so on and so forth. But unfortunately, time will not allow for that. So this is pretty much a bare bones treatment of transmission line theory. Please do ask yourself, do I know why transmission line theory is important? When wavelength starts being important, right? And when phase starts being important. So ask yourself this question. Ask yourself, how is this voltage linked to the integral of the electric field from some reference point to some point R? What does V of R mean? What does V of Z mean? Ask yourself, how are these electromagnetic waves propagating within these conductors? We've done a proper wave treatment, so we know that you only get appreciable penetration as far as the skin depth of the conductor. Then ask yourself how transmission line theory is linked to Maxwell equations, because there are lots of parallels. I mean, we came up with these wave equations for in transmission line theory, and we also came up with wave equations when we solved the Maxwell equations. So there were lots of parallels between them, and transmission line theory was essentially some sort of special case of the general Maxwell equations treatment. So I hope that most of this is clear, um, and I would be happy to take any questions. Um, the bulk of our transmission line work has been adapted from chapter 10 in David in your Hyatt textbook, Engineering Electrodynamics. It's chapter 10, transmission lines. So yeah, that's pretty much everything that we can and had to cover in this time. Thank you very much for listening. I hope things are more or less clear, and I'll be happy to help you as best as I can. Whenever you want to contact me, just email me at amar.ahmed@lums.edu.pk or whatever, right? Thank you very much.